All right, let's just dive right into this. Welcome to today's explainer on how our immune system actually fights off infections in real time. Usually when you learn about this stuff, you just get handed this massive, overwhelming list of cells and proteins to memorize. But today, we are completely throwing that out. We're going to look at immunity through a totally different lens, the lens of time. Because really, that brings us to the core mystery of this whole explainer. Think about it. From the exact moment a microbe enters your body, all the way to the memory it leaves behind after the battle is won, in what order do things actually happen? We really need to shift our focus away from just looking at a static list of biological soldiers and look at the crucial dimension of time. Because honestly, understanding when things happen is literally just as important as understanding what is happening. So here is our chronological roadmap for this explainer. We're hitting immediate defense, within hours, days later, contraction, and finally, memory. And that gives us this big picture timeline. Just take a second to appreciate the massive scale here. We're spanning from literally 0 minutes all the way out to a year or more. This right here is the fundamental chronological framework of your body's immune response. Okay, let's start right at the beginning with section 1, immediate defense, ready at T0. So what exactly happens the split second a pathogen breaches your body? Well, you simply don't have time to forge new weapons. You have to rely on the bouncers already at the door. We're talking about your physical barriers, like your skin, mucus that physically traps invaders, and defense proteins just floating in your blood. Your tissues even have these cells called macrophages already stationed there like security guards, just waiting to spot trouble. And honestly, they block the vast majority of infections before you even realize you're under attack. So, the crucial point to take away here is that the absolute fastest immunity isn't created after an infection begins. It's the defense that was already prepared before it even started. I mean, if these physical barriers hold up and this immediate defense does its job, you might not even need a massive inflammatory response. The battle is totally won before it really even begins. But, what if those initial barriers are bypassed? Well, that brings us to section 2. Within hours, the innate system expands. Right, so if a microbe actually manages to sneak past the gates, the body triggers this incredibly rapid, highly ordered crisis response. First, tissue cells detect the damage. Instantly, inflammatory signals go off like a biological fire alarm. It's crazy. Your blood vessels literally change their physical structure to open up, and white blood cells are aggressively yanked out of the bloodstream straight into the combat zone. Let's take a look at exactly who is rushing to the scene. These are your early responders, the ones making up the innate response. Neutrophils are typically the very first ones to arrive, and they mobilize in massive, massive numbers. Following right behind them are the monocytes, which step in to help clear out the microbes. And by the way, this aggressive rush of cells into the tissue, that is exactly what causes the redness and swelling you actually see on your skin when you get a paper cut. Now, while these cells are working furiously to suppress the microbe, they aren't just fighting. They're actually buying time and setting up the crucial signals for the next major phase of our timeline. Which takes us away from the infection site and over into the lymph nodes for section 3, days later, adaptive immunity emerges. Now, to understand exactly why this next phase takes several days to ramp up, we really have to look at something called clonal expansion. Think of it like a biological printing press. A single activated lymphocyte divides multiple times to create a massive army of effector cells, and they all have the exact same target specificity. You see, the precise, naive T cells and B cells that are perfectly tailored to fight this exact microbe, they are incredibly rare. They need time to be found, activated, and then physically multiply. Comparing these two states really puts the sheer scale of this into perspective. On one hand, you have your naive lymphocytes. Like we said, they're extremely rare, totally unactivated, and just kind of circulating around in tiny numbers. Basically, they're just potential energy. But on the other hand, after days of clonal expansion, you have the effector cell army. Now, they are massively multiplied, highly targeted, and aggressively defending your body. Your B cells are turning into plasma cells that just pump out antibodies, and your T cells are out there directly destroying infected cells or supercharging the rest of the immune system. And this brilliantly illustrates a massive misconception we need to clear up. Innate and adaptive immunity do not just tag team and swap out like players in a relay race. They overlap. As the adaptive immune system ramps up, it actually enhances the innate system. Antibodies literally make it easier for those innate cells to consume microbes, and the T cells supercharge the macrophages. It's this continuous, overlapping wave of defense, all working together for maximum precision. Okay, so the battle is won. The pathogen is completely cleared out. What happens next? Let's move to section 4, contraction. The criticals stand down. I absolutely love this quote from our source material. In the original text, it reads, 면역 반응은 켜지는 것만큼 꺼지는 것이 중요하다, which essentially translates to, turning off is as important as turning on. And if you think about it, that makes total sense. If millions of highly aggressive, activated immune cells and massive inflammatory signals just stayed at the party after the infection was totally gone, well, they'd start trashing the house. They'd start destroying your healthy tissue. It would be a massive drain on your energy and honestly incredibly dangerous for you. So because of that, contraction is an absolute biological success. It is not a failure, and it is definitely not a retreat. By actively reducing the number of those effector cells and dialing down those blazing inflammatory signals, your body successfully restores its normal, balanced state, what we call homeostasis. Just getting back to normal is the ultimate goal of the entire immune response. But the immune system doesn't just forget, and that brings us to our final section on the timeline, memory, what is left behind. See, not everything disappears during that contraction phase. A small but absolutely vital fraction of those perfectly tailored, antigen-specific B and T cells actually survive. They transition into these long-living memory cells. On top of that, certain plasma cells stick around, continuously secreting low levels of antibodies in the background. What this means is that a biological trace of the infection is permanently recorded in your body. And if that exact same pathogen ever dares to return, well, this completely alters our timeline. Now, what's really interesting here is the stark difference in the data. Look at the primary immune response. It's low and it's slow. Why? Because it literally takes days to build up that army from scratch. But then, look at the secondary response. Because those memory cells are already there, just waiting, the reaction is massive and incredibly fast. It's so fast, in fact, that the pathogen is usually destroyed before it can even make you feel sick. And guys, this is exactly how vaccines save lives every single day. Vaccines effectively hack the timeline by changing the starting point. By safely introducing your body to a completely harmless version of the pathogen, your immune system goes ahead and creates those memory cells. So if you ever face the real dangerous virus out in the world, your body completely skips that slow primary phase and jumps directly to that vastly faster, much stronger secondary response. It's a real game changer. So this single antibody curve essentially tells the entire dramatic story of your immune system. It proves specificity, tailoring responses to distinct threats, say virus X versus virus Y. It proves memory, launching vastly faster secondary attacks. And it proves contraction, intentionally dropping those levels back down to restore your vital biological balance. We've really seen today that time is not just background noise, right? It is a truly critical part of the immune response. A slow response can mean serious disease, while a fast response means health. So when we're looking at immunology, understanding our very survival requires us to always ask two questions simultaneously. What is responding and when is it responding? It's the kinetics, that time axis, that takes standard biology and turns it into a thrilling, dynamic story of survival. But tracing this whole timeline leaves us with one incredible mystery. If the adaptive immune system is so highly tailored, how does it actually recognize one specific target out of the countless microscopic threats out there in the world? How does it know exactly what to attack? Well, that is a fascinating question, and it's exactly what we'll be exploring next time. Thanks for joining me on this explainer, and hey, keep asking questions.